See, did we do the concept test for the capacitors? No, we didn't do that at all. Let's do that then. We've done all these. Y'all had a good weekend, by the way? Yeah. Not sure that we're ready for a full week, but all right. So we have capacitor C1 connect across battery 5 volts, identical connect across battery 10 volts. Which one has the most charge? It's a very similar question to this previously. Two identical capacitors, one on a 5 volt battery, the other on a 10 volt battery. Which has the most charge? It's supposed to be 10 volt. Hard to jumpstart after the weekend, huh? I said it's hard to jumpstart after the weekend. The charge on a capacitor is Q equals CV. So if I have identical capacitors, C is the same for both, but V is different for them, how does their charge compare? Which one has the most charge? Capacitor, first capacitor hooked to the 5 volt, second capacitor hooked to the 10 volts, the same, or can you not tell? Alright, just a few more seconds, I'll stop. 158. B is the right answer. What must be done to a capacitor in order to increase the amount of charge it holds? Do I increase the area of the plates? Move the plates closer together? Do I make the plates smaller? Or is it A or B, or B or C? Guys, I opened this window. If y'all get cold, just let me know. I'll shut it, okay? I opened the window. But if you get cold, let me know. Remember, we have this expression. Alright, so a few more seconds. I'll stop at 102. Alright, very good. So if I make my area bigger, if I make those plates bigger, that increases the capacity of this charge that it can store, or if I move them closer together. So if A goes up, C goes up. If D goes down, that means C goes up as well. Right. Parallel plate capacitor has a voltage of 400 volts, and it stays connected to the battery, and then you double the spacing, what happens? So you're always going to have 400 volts across this capacitor. You double the plate spacing, make them farther apart, what happens? Looking at two expressions here, Q equals CV, and C, so not A over D. Double this, keep this constant, what happens to either the charge or the voltage? All right, I'm going to stop at 115. 115. I think that's right. See, so if I double my spacing, if I increase this by a factor of 2, the capacitance goes down by a factor of a half. And so if this goes down by a factor of a half, that has to go down by a factor of half. So C was the right answer. That's what I marked, C. Yeah. All right. Here I have a capacitor. It's hooked up to a voltage supply, and then I disconnect it. So when you hook it up to that battery, it charges the capacitor, and then when you take the capacitor away, it retains all of that charge. So the charge now remains constant. But what happens if you double the plate spacing to the voltage? I'm keeping the charge constant, and if I keep the capacitor the same, I'll have 400 volts across that capacitor. But what happens if you change the capacitor? You double the plate spacing, double D. Stop at 145. 145? Just guess if you don't know. We had a similar question to this. Is that right? A similar question? Alright. Okay, let's see. So here if I double my plate spacing, how does that affect the capacitance? Does the capacitance go up or down if I double my plate spacing? It goes down, right. So if I make this bigger by a factor of 2, this goes down by a factor of a half. So my capacitance decreases by a factor of a half. And now what we're saying is that the charge remains constant on this, and I want to know what happens to the voltage. Let's try that one more time, okay? So keeping that charge constant, what happens to the voltage? All right, I'm going to stop at 20 seconds. 20 seconds. Doing pretty well. All right, good. D is the right answer. So here, if my capacitance goes down by a factor of 2, if this remains constant, that means our voltage has to go up by a factor of 2. So where on this capacitor I did have 400 volts previously, when I change the shape of the capacitor, I now have 800 volts because the charge remains constant. And we'll come back to this. We're going to start on circuits today. The next couple of chapters actually will deal with circuits. We'll deal with capacitor circuits now, and then we'll go into resistor circuits. We'll look at just resistors in series and parallel. And then later we'll come back and we'll look at RC circuits, resistor capacitors. That is circuits with both resistors and capacitors. I'm going to open this one. Yeah, it's boiling hot here. Okay. Well, let's try. We have another quick test question. Let's do this one. This one's in your book. Here you're just calculating the capacitance. Just make sure you remember how to do this. I'm going to give you epsilon naught here. It's 8.85 times 10 to the minus 12. It's on your equation sheet, of course. Don't forget your dielectric constant there. That's your kappa. Here we have a couple expressions for capacitance.
C is epsilon naught A over D, or a more general term is C is kappa times that capacitance. So if I define this as C naught, I think this is how it's written on your equation sheet actually. If this is C naught, it's epsilon naught A over D, and then my capacitance is whatever my dielectric constant is times that C naught. Pretty sure that's how it's on your equation sheet. All right, I'm going to stop at 3 minutes. 3 minutes. You could see a simple free response question on the test. Just I give you the dimensions, ask you the capacitance. So B is right. So I just say 8.85 times 10 to the minus 12 times the area, which is 0.4 over 1 times 10 to the minus 6. That's the distance. And then you also want to multiply this times the kappa, that dielectric constant, and you get 5.3 times 10 to the minus 6, which is B, 5.3 microfarads. Josh?
On the first sentence, it says 0.4 meters squared each. That would be your area. You wouldn't double it.
No, you don't double it. The area just refers to the area of one of the plates. All right, guys, we're going to move on to circuits. How many of y'all are in the lab? Or how many are you not in the lab? Just a couple of you. Okay, those of you in the lab have already started on resistor circuits. I'm pretty sure, right? I've done resistors in series and parallel as well. So unfortunately, there aren't good lab experiments to do with capacitors. You'll sort of be at an advantage, but also a disadvantage if you've seen resistor circuits, because they're similar, and the way you work with them is similar, but they're also a little bit different. In fact, sometimes they're backwards from the way resistor circuits work. So I'm not sure if it's an advantage or disadvantage to you, but I think it's probably an advantage overall. But we'll spend plenty of time on them, so if you're not in lab, it's okay. We're going to look at circuits this chapter, next chapter, and the next. We'll see a number of different types of circuits. Just sort of the symbols that we'll use are for a battery or a power supply. The symbol that I'll use will look like this. A big line, a little line, parallel to one another. I'll usually put the voltage of that power supply. When we draw this, the symbol refers to the big side as the positive side, and the little side is the negative side. So the big side is the high potential side, and the little side is the low potential side. You'll sometimes see these also written denoting that where you have a positive and a negative, just showing that one side is the positive side. Like on a battery, you have a positive and a negative side, and sometimes you'll draw the symbol with a positive and a negative like that. For the capacitor, I'll draw a capacitor just as two parallel plates, as we've been doing. you'll usually put the capacitance, say 4 microfarads or whatever. Although in other cases, I won't use it in this class, but sometimes you might see a capacitor drawn like this, where it's a curved line and a straight line. I think probably in engineering this is more common to use this type. And those of you in engineering, especially going to electrical engineering, I think otherwise, you might take a circuits class. Does anybody know? Don't take a circuits class? Engineers? Yeah? Okay, I think you probably will. Where you'll deal with these in more detail. And then also resistors. Resistors are just a squiggly line like this. You'll have the resistance written next to it. I don't think there are any other resistor symbols that are used. I'm pretty sure that's the only one. All right, we'll deal with these first two in this chapter, and then we'll get into this in the next chapter. All right, we're going to deal with combinations of capacitors. We'll look at capacitors in parallel and then also in series. Let me just sort of lay them out for you here. Capacitors that are in parallel look like this. All right, and then capacitors that are in series look like this. The way that you can tell a parallel circuit, it seems really obvious that these two are in parallel, I think, right? Because they run parallel to one another rather than running one after the other. But the way that you can tell when you're in a circuit, sometimes it won't be so obvious, is that you travel along through the wire, through these lines, and whenever you come to a point where the wire splits into two pieces, then that signifies to you that you have a parallel circuit. So I notice that this point breaks into two parts, splits into two pieces, and then over here it comes back. Those two pieces rejoin, and so that gives us a parallel circuit, or it tells us that we're dealing with a parallel circuit in between those 2 points. And then with the series circuit, we don't have those splits, so we know that it's in series when I just go along and there are no splits in the wire. We'll deal with combination circuits soon, probably today or maybe the next time, where these circuits actually, you combine parallel and series. I think those of you in lab, if you haven't done it, you will soon do combination circuits, but for resistors. These are kind of fun. Like I don't really like the first couple of chapters, although I thought the Gauss's law and stuff like that, I sort of thought that was kind of fun. I'm not sure that y'all did. What? It was exciting, yeah. But I really like circuits. I think they're kind of fun. It's sort of like a puzzle that you're trying to put together or take apart. And there are really only a few simple rules. And once you get those rules, it's sort of like Sudoku, right? Y'all like Sudoku? Yeah, it's like that, right? So if you like Sudoku, you're really going to like circuits. All right, so let's look at capacitors in parallel. As we go along, we're going to develop a few rules for capacitors, and I'll sort of revisit them from time to time, and at the end I'll put them all together and put them like in a little table for you. So capacitors in parallel. Imagine I have this circuit. Here I have two capacitors in parallel, but of course I could have as many as I want. I could have an infinite number. When capacitors are in parallel, they have the same voltage. So for example, if I have a 12-volt battery here, then I also have 12 volts across this capacitor, and I have 12 volts across this capacitor. All right. However, if two capacitors are different, it should follow that they have different charges, even though they have the same voltage. All right, and that's because of this basic rule that we had before for capacitors, that Q is equal to C times V. All right, so if I have two different capacitors here, they both have 12 volts, but let's say that one of them has a capacitance of 1 microfarad and the other has a capacitance of 2 microfarads, then they're going to have different charges on them. For example, this one will have Q equals CV. That's 2 times 12, or 24 microcoulombs. This one I have 12 microcoulombs. All right, so capacitors in parallel have the same voltage They don't necessarily have the same charge, but their charge is given by Q equals CV. You can sort of imagine, this always helps me to imagine that when they're hooked up in parallel, they have the same what in parallel? They have the same voltage. That'll be very important later when we come about this. When they're hooked up in parallel, it's sort of like they're hooked up to a battery. So this is my battery. I have one capacitor there, and then I have one capacitor there. Those two capacitors are in parallel, right? And so if I have a 12-volt battery, then it's like each of these capacitors is hooked up individually to that battery. So they each have 12 volts to them. By the way, our households are laid out in parallel as well for that reason, so that everything in your household will have the same voltage, and you won't be dealing with different voltages throughout your house. We'll deal with household circuits in a couple of chapters. We'll look at circuit breakers and how your house is laid out and other safety devices. Alright, so let's just do this very simple capacitor circuit. I just want to know what is the charge on C1 and C2. What's the charge on this capacitor? 10 microcoulombs, right? And this capacitor is 20, right? That's simple, right? Yeah, probably not going to see a straight up parallel circuit on your test. We'll have a combination circuit. We'll do a couple of different examples. But this is sort of the basic building blocks of that. So here I have 10 volts. I have 10 volts here. So I'm going to have Q equals CV. That is 20 microcoulombs here and 10 microcoulombs here. Okay, yeah, so Q1 is C1 V1. That is 1 microfarad times 10 volts, which is 10 microcoulombs. And then this is C2 V2, which is 20 microcoulombs. Anytime you have two or more capacitors that are in series or in parallel or in a circuit in general, you can replace them by a single capacitor. We call this an equivalent capacitance. As you're in the lab, you did equivalent resistors, and this is where the problems might come up, because what you did for resistors is going to be exactly opposite what we do for capacitors. So this is called the equivalent capacitance. And for capacitors in parallel, the equivalent capacitance is just going to be C1 plus C2 plus ... however many capacitors you have. Alright, so for example here I have this 1 and 2 microfarad capacitor. What's going to be my equivalent capacitance here? If I were to replace those two capacitors with a single capacitor, what would my equivalent capacitance be? 3 microfarads. It's just 1 plus 2 is 3 microfarads. So my equivalent here is just C1 plus C2, which is equal to 1 plus 2, or 3 microfarads. Let's see. We'll come back to this. I'm going to sort of summarize the rules that we have for capacitors in parallel. And I'll come back later when we do capacitors in series, and I'll rewrite these all together. But let's write some rules for capacitors in parallel. All right, first of all is that the equivalent capacitance is equal to C1 plus C2 plus however many capacitors you have. That's the first rule. The second rule is that caps in parallel have the same voltage. The third rule is just this basic definition for capacitance, that Q is equal to CV. And then there's a fourth rule. I'm going to sort of put it in a little thought bubble because I never really use it. But we'll see that there's a similar rule for capacitors in series. So I'm going to write this here just for completion, for completeness. That is that the charge on the equivalent capacitor is equal to the charge on the individual capacitors. Let me show you what I mean by that. So for example, up here, this equivalent capacitor, let's say that I have 10 volts up here, so I have 10 volts here. That means that I have Q equals CV, which is 30 microcoulombs here. All right, but as we've already done here, I have 20 microcoulombs here, and I have 10 microcoulombs here. So that fourth rule is just saying if I have 30 microcoulombs here, then the sum of these have to add up to equal the charge on the equivalent capacitor. That's what that means. We'll see this with series. There's something else that adds up. Our voltages will add up to equal the total voltage, and that's a more useful rule, but I don't think you'll ever use this. That's why I put it off bubble. All right, let's try this quick test. What is the charge on the 3 microfarad capacitor? See, I will make it a little smaller. It's the charge on that 3 not micro, but that 3 millifarad capacitor. Should be pretty easy. Battery. All right, I'm going to stop at 120. 120. Almost everybody has the right answer, so if you're not sure, just ask your neighbor. 120. All right, B is the right answer. I have 18 volts across each of these capacitors, so that means I have 18 volts here, and I know that Q is equal to C times V, so that's 3 millifarads times 18 volts, that's 54 millifarads. So B was the right answer, 54. Right, those are pretty simple. Likely not to have just a straight up parallel circuit. All right, well, let's look at series circuits. Capacitors in series all have the same charge. You can think about this in terms of like induction, charge by induction. Remember, if we had, like, say, a charged metal sphere, let's imagine that we have a charged metal sphere, and let's say that it has a certain charge on it, negative Q, right? And then I bring up another sphere up next to it, then I'm going to get this charge that's induced on this second sphere, where I'll have a positive Q over here and a negative Q over here, where those charges will separate because of this charge by induction. We sort of talked about this before, but that's largely what's happening inside of a capacitor. That if I hook these capacitors up to a battery, this battery sets up a positive Q charge on this plate, and then all the electrons that are contained in this central portion, the electrons come over here and leave me with an excess of protons on that plate, and such that I'll get plus Q, minus Q, plus Q, and then I'll get minus Q. So this is largely charged by induction that I'm setting up through this battery. And because of that, it doesn't depend on the capacitance of the capacitor. All of your capacitors in series will have the same charge. So remember, for our capacitors in parallel, always have the same what? Voltage. Capacitors in series always have the same charge, right? So capacitors in series always have the same charge. However you want to think about it, doesn't matter. I like to think about it in terms of induction, but just remember, capacitors in series always have the same charge. So that's our rule number 1. I'll rewrite these in just a little bit. Our rule number 2 is that the equivalent capacitance is given by this. 1 over C1 plus 1 over C2 plus ... In your equation sheet, it's given this way, that 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2. Those are equivalent, right? Because if I take the inverse of this side, I take the inverse of that side, and I get this expression. I'll be using this, but just be aware on your equation sheet, this is what you have. But by the time the test comes, you don't really need this in the equation sheet anyway, I think. So anyway, that's my equivalent capacitance for capacitors in series. For those of you that are in the lab that have done resistors in series and parallel, you have a very similar expression for resistors, but this is for what resistors look like. Parallel, right? So resistors in parallel look like capacitors in series when it comes to the equivalent. So be careful with that, it's a little bit different. That's on your equation sheet, and it's what it says for parallel. But just be aware of that as you go along. Alright, so that's my second rule. I like to use really simple numbers, so just sort of get a feel for the numbers that I use, just to make your math easier. So for example, I like to use 3 and 6 a lot. There are other pairs of capacitors or resistors that I like to use just that make this dealing with fractions a little easier. So just right now, go ahead and try to take the equivalent of this, a 3 and a 6. That's 1 over 3 plus 1 over 6. What is that? Don't use a calculator, just use the fractions. Nice round number. What is 1 over 3 plus 1 over 6? Remember, you have to find the greatest common denominator. It's going to be 6. It's going to be 2 6 plus 1 6. And then 1 over whatever that is. What is that equal to? Is equal to 2. Right. So just be aware. I like to use these simple numbers. It'll make you a lot easier when you're dealing with a test, so you don't have to worry about your calculator or finding the right answers. That's going to be 1 over 2 6 plus 1 6, which is 1 over 3 6, which is 1 over a half, which is 2. So the equivalent capacitance of these two capacitors is 2 microfarads. Other pairs that I like to use, by the way, like for example, if I have a 4 and a 4 together, that's going to be 1 over 4 plus 1 over 4. What is that? That's also 2, right? If I put a 2 and a 2 in series, what does that equal to, the equivalent? It's 1, right? That's 1 over a half plus a half. That's equal to 1. Let's see, if I put, what is it, a 3, a 6, and a 12, I think? Is that right? What is a 3, a 6, and a 12? That's going to be 4, 2, I forget. There's another one with 3. You'll see that as we go through the examples that I use these nice round numbers. There aren't that many pairs or triplets that I can use, but just sort of be aware of that when you get to the test, so you're not fiddling around with fractions a lot. All right. Okay, and then also the charge that is found on both C1 and C2 is also on the equivalent capacitance. I'll show you what that means. Let's do this example. So here I want to find the potential difference across C1 and C2. Actually, let me go back and revisit this. So if I have two capacitors in series, they both have a charge Q. Right? That's our first rule. Capacitors in series have the same charge. If I put those two capacitors into an equivalent capacitor, it's also going to have a charge Q. So the equivalent capacitor has the same charge as whatever capacitors that are in series. All right? We'll see that. Let's do this example. I'm going to do this example the hard way, and then we'll come back and do it the easy way. Okay? Here I just want to know what is the potential difference across both C1 and C2. So I want to know what is this potential difference, and I want to know what is this potential difference, V2. I'm going to make this 12 volts here instead of 8, okay? So I want to know what is V1 and what is V2. We'll do it the hard way first. First, I want to know what is the equivalent capacitance. That's going to be 1 over 2 plus 1 over 4. That's 4/3, is that right? Yeah, 4/3 microfarads. And so I can redraw this circuit as just a 12-volt battery with a 4/3 microfarad capacitor. All right. I can find the charge on this capacitor. I'm going to call this equivalent charge. That is, what is the charge on the equivalent capacitor? And that equivalent charge is equal to C times V, which is 4/3 microfarads times 12 volts. That's what, that's 416 microcoulombs. All right, but that means that I have 16 microcoulombs on both Q1 and on Q2. All right, so capacitors in series have the same charge. So that means our equivalent charge is 16 microcoulombs. So V1 then is Q1 over C1. Remember, Q equals CV. That's 16 microcoulombs. What was C1? Yeah, C1 is 2 microfarads. So that's equal to 8 volts. And then V2 is Q2 over C2. Just 16 over, is it 4 microfarads? Yeah, 4 microfarads, which is 4 volts. All right, so sort of the long way, whenever you encounter capacitors in series, is that you find the equivalent capacitance, then you find the charge on that equivalent capacitance, and then you recognize that that same charge is on all the capacitors, and then you can find the voltage. The easier way, especially when you have a capacitor like this, we'll invoke our third rule, which we'll come back to. I'll write it in a second, but let me just show you this. Our third rule is going to be this. This is our fourth rule, actually, is that the total voltage equals the sum of our individual voltages. I'll write them all on the list in just a second. But our fourth rule is going to be the total voltage equals V1 plus V2. So I know then that the sum of these voltages has to equal 12, which is what we found. Right? We found this to be 8 volts, and this one to be 4 volts. So we know that the sum of those voltages have to add up to equal 12. So you could come to this, and hopefully you'll be able to look at circuits like this by the end of a couple of chapters, and just be able to look at these two capacitors and say, well, I know that this capacitor is smaller, so it has to have a bigger potential. I know that because of this relationship, which is our third rule, Q equals CV. They all have the same charge. If C is small, that means V is big. Okay? So if C is small, it means V is big. So this one has the bigger voltage by a factor of 2 because it has a smaller capacitance by a factor of 2. This is different for resistors, by the way. It's a different relationship between voltage and resistance than voltage and capacitance. Alright, so here I should have a bigger voltage here and a smaller voltage here. So I have 8 volts here and 4 volts here. I know it's bigger by a factor of 2, and I know that the two numbers have to add up to equal 12. So I wouldn't have to go through all that business, the equivalent capacitance, equivalent charge. I could just look at it and say, well, I have 8 volts and 4 volts. Hopefully you'll get to that point where you'll be able to do that. It's okay if you don't. Like, you can go through all those steps, but it's a lot easier if you don't have to. All right? So, let's see. C1 has half the capacitance. This is what I just said. C1, which has half of C2, has twice the voltage. All right, so Q equals CV. If I have a small c, that means I have a big voltage. It's an inverse relationship between C and V. And then also when capacitors are in series, there's some of their potentials that is, the sum of their voltages, or their potentials, is equal to the total. And that's our rule number 4. That is that V total is equal to V1 plus V2 plus V3 plus ... All right, let me just sort of recap those rules for all of them. So, for capacitors in parallel, I have several rules. First, the equivalent capacitance is C1 plus C2 plus however many capacitors I have. The second one is that, what was the second one? Oh no, this was the second, I'm sorry. Can I reorder them? I get messed up if I don't, I'm sorry. The second one is the equivalent capacitance. Is that right? Oh shoot, I'm sorry. It's Monday, right? Y'all look like it's Monday too. So equivalent capacitance is C1 plus C2 plus the caps in parallel have the same voltage. For capacitors in parallel, what was the third rule? Oh, Q equals CV, yes. And then the fourth one, which we don't really use, but is that the total charge, or the equivalent charge, let's write it like that, the equivalent charge, that is the charge on the equivalent capacitor, is equal to the sum of the charges on the individual capacitors. Not really a rule you use that much, but, you know, impress your friends with it. For series, equivalent 1 over C1. They have the same charge. Third is the same. And then the fourth has to do with these potentials. The total potential equals V1 plus V2 plus ... Alright? So those are our rules for capacitors in parallel and capacitors in series. Resistors will have a similar set of rules, but they'll be a little bit different. Alright? Okay. Let's see. Can I go down from here? First, let me ask you a question. This will prepare you for your calculus test. What do you get when you take the diameter, or no, excuse me, the circumference of a pumpkin and divide it by the diameter? Pumpkin pie. Very good. Had you heard that one, or did you just get it?
No, I just...
You get it? Circumference, diameter, pumpkin pie. All right, good job. All right. When is your test anyway? What time? It's in 20 minutes. All right, I'll let you out in just a few minutes. Let's just do this quick test, then we'll go, okay? All right, what is the potential across the 24 microfarad capacitor? By the way, guys, you should be able to get rid of 2 answers right away. Which ones? 18 and what else? 29, right. Because I know that the voltage here can't be equal to or greater than this. Because it has to add up to something. Also know, I'm going to help you out with this. This one is going to have the biggest or the smallest of all the voltages. It's going to have the smallest of all the voltages. This one's going to have bigger by how much than this one? Twice the voltage. This one has 4 times the voltage, and this one has 6 times the voltage. You might be able to figure out the answer just from that information without going through what is the equivalent capacitance and all of this. already got rid of A and B. I'm going to sort of outline the long way to do this, and then afterwards I'm going to show you the easy way, okay? So, keep doing what you're doing. Wait, that's not right. All right, almost everybody has the right answer. I'm going to stop at about 305. Just ask your neighbor if he's not sure what it is. 305. 305. Okay, very good. C is the right answer. Look, you find the equivalent. What's the equivalent of this? Anybody know? The equivalent capacitance. Did you get it quick? Huh? Is it? No, it's not 2, is it? Seriously? Okay, the equivalent is what it is. I don't know. You do that 1 over 3 plus 1 over...
1.6.
1.6? That sounds about right. Alright, then you find the equivalent charge. You say 1.6 times 18, and that gives you the equivalent charge. And then you say whatever that is divided by 24, that'll give you 1.2 volts, right? That's sort of the long way. That's the way we did before. The easy way is to say, well, it's one of these. I'm not sure which one it is. I think it's probably the smaller of the two. And I say, well, let's say if this is 1.2 volts, let's just guess. Then I know this has to be 2.4 volts. This has to be 4.8 volts. And this has to be 7.2 volts. And then you add all those up, see if they add up to 18. And they do, in fact. So that's sort of the easier way to first do it, is to get rid of the big answers first, and then pick between one of those two, and look at how they're distributed, the capacitances, and you can find the answer. We'll do more of those next time. Good luck on your test today, okay? Thanks for coming to class. I know it's tempting to not, to just sleep in or study or whatever, but